Good morning. Today we are discussing about the automatic generation control. It is coming under your fourth module, and in the previous lectures we have considered how we are explained about how we are constructing the block diagram or how we are representing the load frequency controller by using a block diagram. We have considered three parts. One is speed governing system, and the second one is turbine, and then we are having this load generator load model. So, and we combined all these three and we got the entire block diagram of the frequency controller. It was coming in our first and second lecture, and in the last or in the third lecture, third and fourth lecture, we have explained about how we are introducing an integral controlling action to this controller, so that we can make that steady state to zero. So all these things we have discussed in the previous lectures. Now we are going for a two-area load frequency controller. That means we are controlling two systems and which are connected to each other by using a tie line. There may be two areas. You can say you know that in our entire electricity regions are considered in our country, we are having so many regions are there. And these regions are connected to each other by these tie lines, and there will be a tie line power flow. So each control area is like a load frequency controller we have studied, and now we have to study about how this tie line power flow is controlled. So we are considering a two area system. That means each one is having a frequency controller. Control objective is now to regulate the frequency of each area. That we have already studied, how we are controlling the frequency of each area, and to simultaneously regulate the tie line power. We have to regulate that tie line power as per the inter-area power contracts. There will be some contracts between these areas. So according to that, this tie line power has to be controlled. In case of frequency, proportional plus integral controller is installed. So as to give the zero steady state error in tie line power flow as compared to the contracted power. Now each control area is represented by an equivalent turbine, generator and governor system. We have studied that our system will be that speed controller or the frequency controllers will be having three parts. One is speed governor system, then the equivalent turbine system and the generator load system. So we are combining all these, then we'll be getting each control area is represented by these systems, and for each area we are using suffix 1 to refer area 1 and suffix 2 to refer area 2. In an isolated control area case, the incremental power, this is delta Pg minus delta Pd, we have discussed about this. It is how this is representing. It is accounted by this rate of change of stored kinetic energy and increase in the area load caused by the increase in frequency. So two terms are there. So in our control also we can in our block diagrams also you can see these two terms, these two signals you can see there. One is representing the increase in stored kinetic energy, and the next one is representing the increase in area load caused by increase in frequency. Since a tie line transports power in or out of an area, this fact must be accounted for in the incremental power balance equation of each area. So for each area we have to consider the same what we have studied earlier, these two factors, that is, one is increase in stored kinetic energy and the increase in load by the increase in frequency. These two we have to consider again. Now we are checking how this tie line power flow is represented. Power transported out of area 1 is given by, that means tie line power from area 1 to area 2. Area 1 having a voltage V1 and 2 having a voltage V2. X12 is the reactance between them. Delta 1 and delta 2 are the power angles of each area, power angles of equivalent machines of the two areas, delta 1, 0 and delta 0. Then this is the tie line power flow for if there is any change in delta, why delta 1 and delta 2 is changed? Because we know that whenever there is a change in frequency, we are now studying about the power frequency control or change in frequency due to the change in steam input. So in the first lectures you can clearly you can understand that. So whenever there is a change in power or steam input or the frequency, there will be a change in delta angle, power angle, delta 1 and delta 2. Then the tie line power can be expressed like this, T12 into delta 1, where T12 is given by this relation. This is known as synchronizing coefficient. Now this point we have discussed earlier. So you remember this one, what is tie line, change in tie line power flow, delta P tie 1 in per unit equal to T12, where T12 is this relation, and this delta 1 can be represented in terms of the change in frequency. Change in power angle can be represented in terms of change in frequency by using this relation. So from this equation we have reached this here. Instead of that delta we can represent it by using the incremental integrals of the incremental frequencies. So this 2 pi into integral delta f1, for each area it will be coming there. The other T12 is already there in our equation. So this is represented by this equation. We can represent the incremental power, tie line power, the change in tie line power can be expressed like this. Delta f1 and delta f2 are incremental frequency changes of areas 1 and 2. Similarly, the incremental tie line power out of an area 2 is given by 2 pi into T21 integral delta f2 dt minus delta f1 dt, where T21 can be represented like this, which can be represented by using the first equation, or T12. T21 can also be represented by using the relation of T12. So we will be getting this PR1 by PR2 into T12, or A12 into T12. Now this is the incremental for the area 1 power balance equation. That means generation minus demand. That is the change in power balance equation. Whatever the generator is generating and whatever the demand, so that difference is the power balance relation. This one we already discussed for the first area to H1 by F10 d by dt of delta F1. This is actually representing the kinetic energy change. So earlier we have discussed that power balance equation is represented by using two parts. One part is change in kinetic energy. So this is the change in kinetic energy part, and this is the change in frequency part. So these two terms we have already discussed in the previous lecture. There will be, for each control area, for each load frequency controller, we will be having two parts. One part is representing the kinetic energy change, and the another one part is representing the frequency change. So the third term is, now we studied what is the tie line power flows, because here we are connecting those two areas by using a tie line. So that change of the power can also be represented here. All the quantities other than frequency are in per unit, and we are taking the Laplace transform. Then will be getting like this Laplace transform, and we are rearranging this. Then we are getting delta f1 of s. We have to get that earlier in the previous lecture also. You can compare with those. All the terms are same only, except there is an extra term here. You just compare with the previous lecture. With only one area, with only one a load frequency controller. If you are considering, then you will be getting the same relations only, except that there is a delta P tie line 1. Now here why we are using KPS1, because KPS1 equal to 1 by B1 from this relation, and TPS1 equal to 2H by B1 into F0. Now compared to the isolated control area case, the previous case, the only change in the appearance is delta P tie 1 of S. Its relation is delta P tie 1 of S is equal to this one. So how we are representing this? Delta Pg1 minus delta Pd1 of S minus delta P tie 1 of S. So delta Pg1 of S minus delta Pd1 of S minus delta P tie 1 of S into this block, into what? Into KPS1 by 1 plus TPS1, into KPS1 by 1 plus TPS1 of 1 to F. This will give delta F1 of S. Similarly, for the control area 2, delta p tie line 2. So the similar same equation only, but now what we have done here is we are represented by using the in terms of T12. So in this previously we have defined that T21 can be expressed as A12 into T12. So here we have represented by using that T21 is represented by using this what A12 into T12. Why we are representing? Because then you can directly take that from the previous one. So here minus 2 pi into T12 by S, minus 2 pi into T12 by S into minus A12 will give what? Delta P tie 1. From this itself, delta P tie 1 of S is what? Delta P tie 1 of S is 2 pi T12 by S into this delta F1 of S minus delta F2 of S. This is delta F1 of S. This is delta F2 of S. So delta F1 of S minus delta F2 of S into this block will be give what? Delta P tie 1 of S. Now delta F1 of S minus delta F2 of S into minus A12. There is only one change between delta P tie 1 of S and delta P tie 2 of S. Tie 1 of S and tie 2 of S. So this is what? Tie 2 of S, and there is only one difference. Here it is minus 2 pi T12 by S into delta F1 of S minus delta F2 of S. Here it is minus 2 pi T12 by S into A12 delta F1 of S minus. So what we are doing is delta F1 of S, delta F2 of S, we are taking the difference and multiplying by 2 pi into T12 by S will give delta P tie 1 of S, and multiplying with a minus A1 by 2, minus A12 will give delta P tie 2 of S. So you required actually you required this block diagram. This block diagram is representing the tie line power flow. So we have to include this tie line power flow in our block diagram. Now this area control error means we have to reduce that error to 0. For that we are employing an similar to that we are here an integral control loop is employed for each area. This is accomplished by a single integrating block by redefining all area controller. So that area, to make that area controller, we are introducing a integral controller. So AC1 area controller 1 for the first loop will be what? Delta P tie 1 plus B1 into delta F1, and we are taking the Laplace transform. For the area 2 also we are taking the Laplace transform. So we are including this one also in our loop, in our block diagram. So what you will be getting here, you have to include that integral block also. So this is the last final block diagram of our two area control system. You can see here two areas. This is one area and this is the second area. So actually I am starting from here. This was our first diagram, frequency controller, an isolated frequency controller without integral controller. So you can see the speed governor system block diagram here, turbine block diagram here, and this our load, generator load block diagram, and how we are getting this delta PC of S 1 by R, all these things we have studied earlier. And now you will be getting a delta F of S from this, that is change in that frequency. That is our output from this first isolated control system, isolated area block diagram for a load frequency controller. In this we are now introducing a integral controller. So this same only, this internal loop is same only. Here what we are doing, just from this delta F of S we are taking a signal, a frequency, it is given to an integral controller. So that integral controller is introduced. So that is the second change we have made. So by this we can make that steady state, that error to 0. So this is the second. So earlier it was only delta PC of S. Here this integral controller is also coming. So we have to compare these two, and it is given as the input. This loop is same only. This internal loop is same only. Now what we are doing, we are considering two areas like this. So this is one area. Similar to this we are considering another area. So you can see the same thing here also. You can see this we are considering the integral controller, and this is our speed governor. Speed governor plus turbine. It is combined actually. That one also we discussed there. This is speed governor plus turbine blocks are combined, and this is the generator block diagram, and this is delta F1 of S, its output. Similarly here also this is integral controller and speed governor plus turbine, and this is the generator, and delta F2 of S is its output. And this delta F1 of S and delta F2 of S is given to this 2 pi into T12 by S, and it is given as delta P, tie line 1, delta P tie 1 of S, and it is multiplied with the minus A12 will give delta P tie 2 of S, tie line power flow for each block. And what we are doing now, and this is again given to an area integral controller. So that we studied earlier. This tie line power is also given to an integral controller. So along with this, we are actually multiplying with the B1 into delta F also. So you can see here AC, area control error for 1. If we are considering 2 areas, means area control error for 1 is delta P tie 1 plus B1 into delta F1. Similarly, area control error for 2 is delta P tie 2 plus B2 into delta F2. So you can see here this delta P tie 1 is taken, and this is delta F1 first from the first block, and it is multiplied with what, B1 into delta F1. Both are added and given as area control error 1 for the first block. Similarly, delta P tie 2 is taken here, B2 into delta F2 is both are added and given as an integral input to this integral block. So you just study like this. This is actually very simple only. From this beginning you study the very simple diagram. The first step you have to study about the isolated system, whatever the blocks are coming there, you study that, and to that we are introducing an integral controlling block, integral block, and to that again we are considering if only one area, means this is enough. Actually this tie line power and all things are not needed, only that integral, up to that integral controller is enough. If there are 2 area systems, we have to combine these two by using a tie line power flow controller. Tie line power flow block diagram is also coming there, and it is also given as an input to the integral controller. So with this this 2 area control system is and the load frequency controller is completed. Actually only one portion is remaining now, this voltage controller, automatic voltage controller. So that I will be taking in the next class.